What I'm going to do today is actually I feel that I kind of rushed through things a bit last time, and it's like a take two of the last time. And it will be more general too, like not just about meshing, but about like a packing covering LPs. That is actually very general. So today we'll learn something that we learned last time, but for something much more general and should be more understandable. Okay. And so, but what I will not repeat from last time is this part. That is, if you consider this process where you start you have to wait for every expert to be one initially, right? And then there are many days, okay? And then for each day, we are given some gain vector h on day t, so ht, and this gain vector is between 0 and rho, where rho can be more than 1. Normally it's at most 1. Here rho is more than 1. And then we also promised you that the expected gain of weight update is at most 1. You see this, right? This is expected gain of the weight update is at most 1. Then given this gain vector, then we just update the weights in this way, multiplicatively. And the conclusion is that just repeating this process for t days, where t is something like rho log n, basically something that is linear in rho. Okay. If you repeat this process, given the gain vector, update the weights multiplicatively according to the gain, again and again. Now, at the end, once you look at this h bar is just the average gain vector for every expert, averaging over all t days. This is just a sum of the gain vectors, and then you average it over t days. If you look at this average gain of every expert, then for every expert I, its average gain must be something like 1, not too much more than 1. And the intuition is just that this is because we know that weight update algorithm has no regret. It has no regret. If the weight update algorithm has small gains every day, then there cannot be any other expert that outperform weight update. So if our gain on each day is 1, then basically the average gain of every expert must be close to 1, cannot be much more than our. Yeah.
So this is kind of a question in general, but I think a few lectures ago we talked about the idea that if the MWU gain is small, then the best expert's gain is small, and if the best expert's gain is large, then MWU's gain is large.
Yeah.
Is the inverse of both of those true as well, or?
Good question. So you ask, right now we just said that if the best the gain of the best you said that right now we just said that if the gain of the MWU is small, then every expert must be small too. The gain of every expert must be small. Now you ask if the gain of every expert is small, must it be that the gain of the MWU must be small as well? I am not sure. Yeah. But good question. Yeah.
I
think it should be the
because
case.
The MWU has to be strictly less than the best expert, or less than or equal to the best expert. Right?
Yeah, I think you're right actually. It should be the case that let me think. So, okay, good. I have the explanation why it's not clear. So first of all, on each day, like what we gain is like an average of each expert. Right, on day T, we gain something that is average, like with respect to some distribution of the expert. But it could be the case that on like, but the power of us of weight update is that it can switch between experts. So it could be the case that like expert 1 gains a lot in the first half, and then expert 2 gains a lot on the second half, and we might like weight update might like gain as much as the first expert in the first half, and then the second half it gains as much as the second half as the second expert. So that's why it's not too clear, but like because we have the like weight update has this power of switching between experts, but it's not like, but it could be the case that you actually have the converse of this claim. So I'm not sure. Yeah. Okay. All right. So okay. So we're gonna just use this again. Okay. Like last time, and I will not prove this. Okay. But today we're gonna learn about packing covering LP. Okay. So packing covering LP is like a subclass of LP. So you know that for every LP you can write it in the standard form like this. This we know. However, for packing LP, just write it in this standard form, except that every entry in A, B, and C are non-negative. This is a restriction. Okay. So if it's a maximization LP, and this is at most, then if all of entry of A, B, and C is non-negative, then this is called packing LP. And it's dual. It's just look at the dual, and this is going to be called covering LP. And it has like a really intuitive name, right? Because here it's like you ask, like you try to pack something into X such that like you need to respect the capacity B, and you want to pack as much as possible. This is like to pack. And this one is just covering, which is you need to find Y such that it satisfies, it covers C. Like it needs to be big enough so that every constraint is more than C. And we want to minimize Y. So we want to put as small as possible things as long as it covers this constraint. Okay. So sometimes people say this is LP. Like in general, they call both of these positive LP for the obvious reason. Okay. But like if you look at like this is, in particular, this is packing, this is covering. Okay. And for any packing covering LP, you can put it into the standard form. Basically, you could scale things down so that this one is like B and C are both 1. And then this is just, these are both 1. These two LPs are dual to each other again. So why you can put it into the standard form like this? Well, like let's look at this. For example, let's look at this transformation. Suppose you start with this packing LP, right? You have some vector B and C, yeah, and A is just some matrix. And let's say that I use this like this matrix A is of dimension B times E, but you don't need to think of V and E as something from the graph right now. I just use V and E because it's more convenient and like it's hard to swap. Like it's easier to remember than M and N because you might get confused. But yeah, there are V rows and E columns. So okay. So I claim that you can actually transform it into another LP where C, the vector C here is all 1. And any ideas how? Not too hard to like say that there is another LP that is equivalent to this one, such that this is 1. Yeah.
Can we scale x? So for every element in C, we scale x down by that C value. And then for every element in A, we would have to do the same. Actually, I don't know how you would scale A, but you would have to do some scaling to the corresponding entries of X
Exactly.
in A. I don't know if it's up or down though.
Yeah. So basically, like you say, scale down, but it's scale up or down. But anyway, it's scale according to C.
Yeah.
Like replace, let's say x prime is just C times x. Okay. So this thing is just then 1 times x prime is just C times x here. Okay. And once you scale x up by C, then you just need to scale A down by C accordingly. So each column of A is now like a scale down by C. So once you have this, now can you make B to be 1? How can you do this? Scale again, right? Just scale every row by B. Okay, that's it, yeah. So for every row, just scale it by B. And throughout, I'm not sure you see this, but throughout this lecture, just to make it more like easier to understand, I don't know, like this one, the bold one is a vector 1. Okay. If it's not bold, then it's just number 1. Okay. So this is some positive, like in packing covering LP. Have you seen, can you tell me some example of LP which is non-positive LP, like non-packing covering LP? We have seen at least one before. Which one is there? Yeah.
Well, from the homework, it was max x min y or min, like that question.
Max x min y.
Or max y.
The simplex vector?
Minimax, yeah, that one.
Minimax.
Yeah.
Yes. Minimax is 1. Exactly. Good. What else? Did you say something, Scott?
Wait, were you asking for examples of packing or non-packing?
Non-packing and non-covering.
I think wouldn't max flow min cut be an example of that as well?
Max flow. Yeah. Max flow is 1. Why? Well, if you look at this thing, you have like max flow. We remember like we have flow conservation and capacity constraint, right? So you have this one. Right now it looks like, I mean, here you see that some of the coefficient is non-negative. It's negative. Here like things looks like non-negative, but if you put it into standard form, you need to move this part to another side, then it would be negative. So there is something negative coefficient, like some negative coefficient here. All right. So max flow is not really like this LP for max flow. It's not packing covering LP. Okay, but let's see that there are many examples that actually you get packing covering LP. So really many problem, really natural one, actually admit packing covering LP relaxation. I said LP relaxation, right? Because it's like it's kind of the integer version, the IP version is like once you, for each problem you need to look at, like you model it as an IP first, and then once you relax it, you get packing covering LP. So the first example would be maximum matching and its dual, which is minimum vertex cover, right? So maximum matching, when you look at its LP relaxation, it's just this one, right? You put fractional value into edges so that the sum of its value on, like, for every vertex is at most 1. Like for every node here, this sum of xe, this thing is at most 1. Okay. And then vertex cover is like this. This is covering LP. Next is like, okay, we can look at the weighted version where the weights are non-negative. The weighted matching, maximum weighted matching, then this thing is just gonna be the weights of each edge. Okay. Then look at its dual. It looks like something similar to vertex cover, except that like for every edge you need to cover it by this much instead of just 1. But this is again like packing covering LP. What if you look at the weighted version of vertex cover, which is here? This is just vertex cover problem, except that for each node, this should be WV. For each node, you have some weight. This is non-negative. This is just, sum covering LP. And if you look at its dual of the vertex cover, it's just this problem, which looks like maximum matching, except that, each node you kind of have capacity that is not 1. There is a name for this problem though. It's called B matching, where B is just to indicate this vector here. This should be WV. Okay, set cover. This is set cover problem. This is set cover. Right. For every element, you need to put like a value into the set that contains the element so that it cover this element. And you want to minimize the size of, like, the total size, the total number of sets that you choose. And then we have seen that the dual of set cover is kind of like element packing. You have seen this. Okay. So like basically a lot of question that we, like natural question that we look at is just usually just like packing covering LP. Okay. But there are some other example, some further example of when you can find exponential size relaxation. Like some problem does not admit poly-size packing covering LP. But if you allow yourself to look at exponential size LP, then you can get packing covering LP. So the first example, there's one example that you have seen. What is that? Like, what is the problem that you can actually find exponential size packing covering LP?
I think it was one of the homework problems, but I can't remember which one.
Yeah, there are several in the homework question. But okay, one that is actually was in the class is just MaxFlow. Like you see that like the standard relaxation of MaxFlow, that was not packing covering LP. But now if you look at this LP relaxation, when we let's say that let PST be the set of all ST paths, right? And now we just want to pack flow value on along each ST path. We want to pack this thing as much as possible, such that for every edge, you have this like the total capacity is at most like the total flow value on this edge is at most the capacity. This is again this is packing covering LP. This is packing LP for MaxFlow. And if you look at its dual, then this is mean cut. But this one is like not exponential, like not polysize because the size of this set is exponential. Okay. Now there are more examples like this is the one in maybe in the homework. If you look at this one, this is from the homework, right? This is like shortest path. This is the covering LP. Right? All the coefficient is non-negative. And what does it ask you? It asks you to find a set of edges, right? Such that like it's like for every ST cut, let's say this is a set of all ST cuts. You want to kind of find a set of edges from S to T, right? Such that for any ST cut, you're gonna hit some edge that cross the cut. So in particular, if you find an ST path, it's gonna hit, like it's gonna cover every ST cut. There's gonna be some edge that go across the set.
This isn't like super important, but I just want to clarify. It's possible for S and T, like the two sets of nodes, to be like disjoint from each other, right? Like there can be an S node surrounded by T nodes. Like it's possible for it to be disjoint.
Wait, like S and T are just two vertices.
Oh wait, I'm thinking of something else. I think like when we were dividing.
Oh, okay.
Like S is in one set of nodes and T is in another set of nodes.
Let's call it A, B.
Yes, yes.
Okay.
Yeah.
Right. Yeah, this is like when I talk about cuts, it's really like a two set of nodes that are disjoint from each other. Like this A and B need to partition the graph.
Okay, they need to.
Yeah. So S is like S here is like A. S is A here. And partial S is just all the edges crossing from A to B. Yeah. From S to outside S. Okay. So this you can see that this is just shortest path. And then once you look at its dual, it's like a problem of packing ST cut. So this is in the homework, so I will not go over it. And this one also is in your homework. A problem of spanning tree packing and global mean cut. Right. So maybe look at this one first. Let's say like that T is a set of all spanning tree. Right. When you look at what this thing asks you is to find a set of edges that it kind of cover. It hit every spanning tree. In particular, if you find some edges that is like a cut, right? If this is like a cut edges, then any spanning tree T must cross it at least once. So as long as you find some cut, like if y here, if the integral version of y correspond to some cut, it will cover, it will hit every spanning tree. And you want to find like a minimum cut. So you see, this is really like a relaxation of global min cut problem. They just find some cut that separate the graph. So that will basically cover every spanning tree. And then if you look at its dual, now it's a packing problem, which is to do what? It's just to try to find like a bunch of spanning trees such that like on each edge, the spanning tree like kind of use each edge. Like the total number of spanning tree that use each edge is just one at most. Like in the integral version, this is like to find like maximum number of disjoint spanning tree, right? You see? If x were integral, it's like to just find this like a disjoint spanning tree as much as possible. But in the fractional version, now you allow some overlapping, but it's a fractional version. Okay. So I hope I like convince you that like this is like some subclass of LP that actually is still very expressive. Okay. And yeah, today, like as I said, it's just a kind of take two of last time. We're just gonna see like a really like a generic way that given any packing covering LP, we can solve it approximately. So the input is you have epsilon and you get a matrix A with V row and E columns, and A is non-negative because it's packing covering LP. Again, A might have nothing to do with graph. I just use it for convenience. Okay. And what we want is to, given this packing LP and its dual covering, we want to compute the approximate solution for both LP. We want to find x and y that is like approximately optimal up to 1 plus epsilon. Right? So that's the problem. Okay. And if you want to be concrete, you can think of this thing as a maximum matching LP, but like throughout the whole analysis, we will really not exploit that it's matching LP. It's just some non-negative matrix. Okay. So that's the goal. And like last time, we will just try to solve the decision version of the problem. Like instead of directly find like the near optimal solution to both LP, we kind of solve the decision version where like we're gonna guess opt. Let opt be the guess optimal value, and we either return a feasible primal solution where the size of x is at least like a opt almost, or you find like a dual solution where the size of its solution, like the value of its solution, is at most opt. So this is just going to be enough because like if you get the primal solution, it means that you know that the real optimal solution is basically need to be a bit more than opt. If you get the dual solution here, it means that the real optimal value must be at most opt, so it must be below. So so if you want to be more like why exactly can you use this decision version, let's say that I have some rough estimate, really rough estimate that we usually can assume that, let's say, like the optimal value is between some polynomial and at most 1 over some polynomial. Like, you think of this as n to the 100. Or if it's like a maximum matching problem, this is at most n, this is at least 1. So just know some rough estimation. And basically, you can just guess the opt. Like guess that opt is like 1 plus epsilon to the I for some I, starting from like this one up to this one. Okay, just start from the smallest I to the biggest I. And like then just feed the optimal, like for each opt, just ask our like feed to the decision version problem, and then ask like whether it return primal or dual solution. So as long as it return primal solution, then we know that opt is too small. Then just increment I, right? And once it return dual solution, just stops. Okay. So basically, you just keep increasing opt. You get primal, and then once you get dual, then you stop. And you know that like the last primal that you get and the first dual that you get, both here will be like a near optimal pair. Like the last primal one will be near like maximum packing solution, and then the next dual one is yet need to be near optimal covering solution. Okay. And yeah, this is a kind of standard thing. And so how many steps do we need? It's just like this many steps. Like from I equals this to this, it's just like basically log of this thing, which is something like O of log n over epsilon. Yeah.
Sorry, the dual here is the minimization.
Yeah.
Right? So then if it's less than or equal to opt, don't we know exactly what opt is once we get the dual?
Say again.
Because opt is the optimal minimization, right? So if the dual solution we get is less than or equal to that, wouldn't the dual solution be exactly equal to opt?
So opt here is like the guess. Right?
Oh, right, yeah.
Yeah. So here we just said that think of this as the estimate. So once you have that, our dual solution is at most this. We just know that like a real optimal solution is at most this guess. Okay. So now, yeah. So this factor is some factor that is kind of standard, and I will ignore this. And actually, we really don't need this decision version, but it just makes things easier to explain. Okay. So from now, we're just gonna focus on this decision version. Okay. And right. Let's look at the oracle problem again, right? Yeah, we will not work with the LPP directly, but we will look at the kind of much easier oracle problem, which I denote by oracle of the weight W. What is this problem? So, well, you're given the weights on each constraint of the LP. And the oracle problem here asks you to find a feasible, like a solution X, such that the value of X is at least opt. And this average constraint is satisfied. It used to have like a many constraint, AX at most 1V, but now we just multiply, we multiply the weight on each constraint. We multiply the weight for each constraint to each constraint here, and just then sum everything up. Okay, this is right. Okay. So you just need to solve this problem or report that no x is like no such x exists. That is, you just report that it's infeasible. Okay, so basically this is just like I just gonna repeat things, right? Like this oracle is like to average the constraint of the LP into the single constraint. And there is two observations that we can make formally. That is like if the LPP here has the optimal value at least opt, then this oracle must be feasible. And why? Well, if there is a feasible primal solution x star of value at least opt, I claim that for every weight W, this oracle of W must be feasible. Well, the reason is that like x star itself is a feasible solution for the oracle. Like if you just take the feasible solution from the original LP, it's going to be feasible solution for the oracle problem too. And because like well, okay, the value of x star is at least up, satisfying the first constraint of oracle. Satisfy this one. How about this one? Well, you know that x star satisfy every constraint of the original LP. So once you multiply W to like once you multiply W to like to the left hand side of both like sides of the inequality, this must be true as well for every W. Okay, so we get that if the original LP has value at least opt, then the oracle is feasible. And the second is that if it's infeasible, then like the contrapositive of this just say that if this oracle is infeasible, it means that the optimal value of primal must be at most opt, right? Less than opt. But here I'm gonna say something a bit stronger than this, the contrast positive here. It says that if actually this is infeasible, we're gonna get directly some certificate. Like this W itself will give a feasible dual solution of value at most opt. So that doesn't just say that the opt is at most, the optimal value is at most opt, but it does give stronger certificate. It gives like a dual solution. So just a bit stronger than the contrapositive here. You see, right? Yeah. Okay. So we get like the certificate that opt is at most, optimal value here is at most opt, because we get the dual solution. How? Well, it said this: if oracle is not feasible, if you look at, let's say W is the total weight, just define Y to be basically W and scale it a bit by opt over W. Just scale version of W here. This is just going to be already a feasible solution of value opt. Okay. So clearly, first of all, we have that the size of Y is just going to be of W, which is opt times W, which is opt. So this is clear, but but we need to say that like so the value is opt, but we need to say that y itself is a feasible dual solution. We need to say that it's feasible. What does it mean to be feasible? It satisfies the constraint, the dual constraint. This is the dual constraint. We need to prove that it satisfies the dual constraint here. So suppose not. Suppose for contradiction that it doesn't satisfy the dual constraint. So there must exist some constraint E prime, right? Such that this is less than 1. Like the coordinate at E prime of this vector is less than 1. If this is less than 1, if A transpose Y at the coordinate E prime is less than 1, then because W is just like a scale version of Y, then you get that A transpose W at the coordinate E prime is at most W over opt. Okay? Because Y is opt over W times W. Okay, so we get that some coordinate of this vector is tiny, it's like small. So now if I just define x such that like x at the coordinate E prime is opt and is 0 at everywhere else, then if you look at this one, right? So this is just like basically sum over all E W E times XE. But we set x to be such that every coordinate is 0 except E prime. So this is just look at this. We just get this one term here. This term is opt. This term is less than W times opt. So this is less than W. So what does it mean? It means that we actually have construct X such that this kind of average constraint is satisfied, right? And also the value of X, the value of X is opt. So it satisfies like a two constraint of the oracle. So the oracle must be actually feasible, which is a contradiction. Okay. Question up to this point? This is, I know it's kind of repetitive, but I kind of really want you to understand this. Okay. Okay, good. So now that we kind of understand the oracle problem, you just think of the oracle problem as easier version of the LP, right? It's just a kind of same problem except that you kind of collapse all the constraints into one. And it's easier to find a solution, first of all. And if you cannot find a solution, then you actually can derive the dual solution. So that's what we have so far. And with this, we are ready to describe the LP algorithm. Right? We have let's say A is a matrix that's describing the LP. Op is our guess. And let's say oracle. Yeah, we have the oracle as a subroutine that defined based on the matrix A and opt and the weights. Suppose that we can implement this oracle. Now we can describe the algorithm like this, just like before. Okay. Just repeat. We initialize the weight to V1. Repeat, repeat for many days. How many days? Something like rho. Rho is just going to be like the width. It's something that we call width. It's kind of dictate how fast this whole algorithm is. So repeat something like day, row many days. And on each day, what do? We just feed the weights into the oracle and then ask the oracle to return us a solution. So the oracle will solve easier version of the packing LP. And if this easier version is not even feasible, then we know that we are done. From the last lemma, we know that it just can return like this thing, basically the scale version of the weight, just gonna give you the dual solution, and we are done. Okay, but if actually this oracle problem is feasible with this weight, then it's just gonna return us some solution for the oracle. This is not gonna be the solution for the original LP yet, right? Because it just satisfies the average constraint, not the original constraint. Like that has many constraints. Just satisfy the average constraint. Okay, so X is like some useful information. What do we do about it? We're just gonna define the gain vector ht to be axt. So like if this is a vector x of size E, maybe this is matrix A, then you multiply it together and then you get this vector ht. Okay. And normally we want that axt is at most 1. This is like what our goal is, right? But suppose I can just promise you that axt is going to be at most row for each constraint. So suppose I guarantee this instead, that ht is at most row. So this is like, I just guarantee you that my solution from the oracle, when I look at each constraint, it might not satisfy every constraint, but still satisfy up to row factor. Suppose I guarantee this. Okay. So this is like I define this how much each constraint is violated to be the gain vector, basically. Okay. And once given this gain vector, I just update the weights, just like from the beginning. Okay. Okay. So we're just gonna repeat this loop for something like row many days. If we can have this guarantee that this is our solution here has like a width at most row. Just repeat, call the oracle. If it's infeasible, it's done. Otherwise, you get some solution. Make it like a compute the gain vector by multiplying to A. Repeat this for t days. And at the end, compute the average solution from the oracle from every day. And then scale it down a bit, then we return that. Is the algorithm description really clear? Question about the description itself? Good or not? Yeah.
I'm a little bit confused about the last step with the final return. So I remember in the diagram earlier where you're increasing the solution basically until you find a dual solution. Why are we taking the average at the end instead of like can't we just use the last solution in the last round as a
Okay.
solution? Why are we taking the average at the end?
Good. So the thing is first, this one is really just for the decision version. This whole algorithm is for one step of it's for decision version. So what you ask is like this each of these step here. Each of these step here is like to call this algorithm just the whole thing for one.
Okay.
Yeah. So it's kind of not really like so it's more like this. If that algorithm return x, then it return the packing solution, then we're just gonna increase our op. And if it's return x again, we increase our op. And until it return y, that's when it return the dual solution. That's when we stop. So that's how it relates to this one. Okay, back to this algorithm. More questions? Okay. Yeah.
Just to be clear, we recompute HT every iteration, right?
Yes.
And it doesn't depend on any of the previous HTs?
No, yeah, like because xt for each iteration can be like different from each other. So we just basically multiply xt to a for every t, yeah, to get ht. Okay. So you see that this whole thing kind of highly depend on row. So row is called the width of this oracle. If our oracle guarantee that row is actually 1, then we actually don't need to do anything, because it's just gonna return like a solution that already satisfy every constraint if row is 1. But row might not be 1, but like the point is like if row is not 1, but like let's say 10, you just need to repeat this loop like 10 log n times. So still not too many times. Okay. So to prove that this thing is like correct, we just need to say 2 things, right? That first, if y is returned, then it's a dual solution with value at most opt, and that we prove. So the only thing we need to show is like if x is returned, then it's a primal solution with value at least like opt times 1 minus epsilon. Okay. So we're gonna prove this, right? If x is returned, then x is a primal solution with value close to opt. So instead of look at x and, we just look at x bar because it's just the scale of x and. And there are 2 things. First, the value of x bar is opt, and this is clear because the value of xt is at least opt. This is just from Oracle promise. And x bar is average of xt. So if the value of xt at least opt and the x bar is average of xt, then the value of x bar is at least opt too. Clear. Next is to say that x bar satisfy all the constraints up to 1 plus 3 epsilon factor. Okay. And here is when we exploit the multiplicative weight update, that if our average gain is small, then the gain of every expert must be small. Right? So just by looking at this H bar, which is the average gain of every expert. Average gain of every expert must, like for every expert, the average gain of every expert is small. So H bar as a vector is smaller than 1 times some like small factor. This is just to say that for every H bar V is at most 1 plus 3 epsilon for every node V, for every index V. Okay. And how to say this? Well, like you know that what Oracle guarantee, right, is that it guarantees this one. This is just like the guarantee of the Oracle. It satisfies its average constraint according to WT. And if you look at this, it's just the same thing as to say that like yeah, that this is xt, so this is ht, and this is what? This is w. So this is just to write that w multiplied by ht over wt is at most 1. That is like the guarantee of the Oracle really just say that the expected gain of, like it's equivalent to say that the expected gain of the weight update algorithm on every day is at most 1. That's what it means directly from the guarantee of the Oracle. So if the expected gain of the of weight update is at most 1 for every day, it means that the gain of every expert must be small, meaning that H bar must be small. Question about this? This is like a kind of the key point why we use weight update at all. Okay. Yeah. So that's how we even like the reason why we even define Oracle problem. We define Oracle problem to looks easier. That is just it's like average, it's collapse all the constraint into 1. But even if this looks easier, it just says something that is really perfect for weight update, which is to say that okay, the gain of weight update on every day is small. That in turn implies that the gain of every expert must be small, meaning that this thing is small. But if H bar is small, then it means that this is small. Why? Because AX bar is just H bar, right? AX bar is just A times the average of X, and you can put, like this is linear, so you can put A in here. So you can just get that this is average of AXT. So this is average of HT, which is H bar. So if H bar is small on every coordinate, AX bar must be small too. Okay. And once we have two things, that the value of this is up and every constraint is almost satisfied. Once you just define xn to be like a scale down of x bar by this factor, we are done. We just get that the value is at least this, and xn satisfy all the constraints. Okay. So to conclude, right? Yeah. the algorithm just either return dual solution of size opt or primal solution of size at least opt over some small thing. And the whole thing, like the whole algorithm, just repeat for something like row iteration. Each iteration just call the oracle and take some time to update the weights. Okay, so what remains is just to implement the oracle. It just depends on like the running time of oracle and by the width of the oracle. If you have done that, you are done. And let's recap, right? If you want to get oracle of width row, basically given any weights, you need to certify this, solve the oracle problem. But to set up the width is at most row, you need this too. That every constraint is certified up to row factor. This is a goal. And one way to implement the oracle is just to of row 1 is just to solve the LP itself. But yeah, that's not useful. So let's try to solve it in a different way. And we have seen like last time that how do we solve the oracle? Well, like if I ask you this, like can you find x such that x satisfy these two constraints? Well, the strategy is just to basically look for the best bang per buck variable, meaning that like it's like x1 here is the best bang per buck variable because it has smallest coefficient, right? It has smallest coefficient in this constraint. So you want to grow x as to be big, but you want this constraint to grow as slow as possible. So you choose x1, and then you just choose x1 to satisfy the first constraint, and then check if it satisfies the second constraint. So that's basically motivate the algorithm. Just set x to be 4, and then check that if x is 4, then it still satisfies this constraint. If so, you're done. If not, like if I change the constraint to be something else, just the same. Look at the coefficient, like look at the variable with the best coefficient, like best bang per buck, which is still x1. Set x to satisfy 6, and then check that it satisfies this or not. In this case, it's not going to be the case. So you say that it's infeasible. Okay. So it means that the standard way to solve the oracle is just to be greedy. Because in the oracle problem, right, the goal is basically the same like in that example. You need to find x. Can someone close the door, please? Yeah. Thanks. So you need to find x with two non-negative constraints like above example. You have that you want a sum of x to be big, and this is just some non-negative constraint. So what we do, just find the variable x e prime, that is like the best bang per buck variable. That is, it has smallest coefficient in this expression. That's all we need to do. In other words, like e prime is like the arc min when you look at w times a, like it has like a minimum coordinate. The w times a, the coordinate of w times a, that is the minimum, is our e prime, and our variable is like x e prime. So just find this e prime basically, right? And then just put value into x prime to satisfy the first constraint. So put it to x xe prime to be opt, the rest is 0, and then check if this last constraint is satisfied or not. So that's the algorithm. Question why this algorithm is correct, or the question of this algorithm.
Just to clarify, so even if there's like a million variables and a million constraints, we just need to like dial in on one variable.
Yeah.
Okay.
So it's one way that makes it work. And next class you see that the width will not be too good, but it still works. Next class we try to reduce the width, but it's okay to just put all into one best bang per buck right now. Yeah.
So as it stands, this algorithm would not fit the width constraint, like we don't guarantee it.
It will satisfy everything except that the width is we can the width is something that we derive from our analysis of Oracle, and as it stands here, the width is going to be a bit big. In particular, it's going to be opt, which is sometimes good, sometimes not too good. Yeah. Okay. So note that we really exploit the fact that LP is packing covering. Where did we exploit it? Yeah.
The non-negative constraints?
Yeah, like that. This is non-negative, and this is non-negative. Like the best bang per buck strategy works when these are non-negative, right? Okay. So that's it. This complete the algorithm, and so far it looks like, because we complete the description of the Oracle, so that complete everything, except that everything is for some LP right now and not so concrete. So let's look at some concrete example. So if we just gonna apply this framework to some concrete problem like max flow or maximum matching, then let's see what happens. So what we're gonna do is look at concrete problem and interpret what happened in the Oracle problem. We just need to see what does it mean to find best bang per buck variable? What's that? And then analyze the width and running time. And then given the Oracle, we plug it into the LP algorithm, like the one that keep calling Oracle problem. And then let's interpret the algorithm. You're gonna see that it's really natural, something really natural, and we analyze the running time. So suppose that we look at matching and vertex cover, right? So we start with this LP for matching. What's the Oracle problem? Well, just need to ask, okay, what's the best bang per buck variable when we try to solve the Oracle problem? So let's say look at this one. This is can be described by some matrix A, and in each round we're gonna multiply some weight. We're gonna introduce a weight and multiply to each. We have weight for each constraint and multiply to each constraint and then sum them up, right? So, what is this thing basically? What is variable with smallest coefficient in this expression for this case, for this when we look at matching? So what we're going to need to do is just basically create WV for each constraint, right? Multiply to this one, and then sum up over all nodes. So I get this thing. This is each constraint multiplied with WV and then sum up. So when I sum this thing up, you can just rewrite, switch the sum and just sum up over weights, over all edges instead. And what's inside here is just gonna be like for each HE, where the endpoint is UV, the coefficient of HE is just this thing. You see, like the coefficient of HE is just gonna be WU plus WV from this one. So to find the best bang per buck variable is then what?
You're just looking at the edge with the smallest WU and WV connecting to it.
Yeah. Like it's like you have it's just to find the HE, the WUV such that the sum of its endpoint is smallest. That's what it means to do, like to find bang per buck, best bang per buck variable. So super simple, right? And what we do is just look at this best guy, put opt value into it, and the rest is 0. So that's how you implement the oracle. You have to wait on the vertices. Find the edge whose sum of the two endpoints is smallest. That's all you need to do on each round. And running time clearly is linear. Can just compute the sum of the weight on every edge. It's linear in the number of edges. What's the width? We need to check like that each oracle solution xt is such that like is this is true. So we need to bound row here, right? How big this is gonna be? Well, what to bound this thing is just to say that for every vertex v, this constraint here is smaller than rho. But how big can this be? Well, this thing is just going to be at most x e prime, because this is the only non-zero coefficient, non-zero variable. This is at most, this is opt. So it just means that rho here is at most opt. So the width is at most opt. How big can opt be for matching? It's at most n, because there are n nodes. It's at most n over 2, actually, yeah. Right? So for matching, like unweighted matching, opt can be at most n. So we have bound the width and running time of the oracle. Once we fit it into the framework, we are done. We just need to wait, like that determine the running time. But let's interpret the algorithm a bit, right? The algorithm basically just say that, okay, find the edge e prime with the minimum weight. In what sense? In this sense, the sum of the weight is smallest. And the algorithm will do what? Will really just update the weight of these two endpoints. Because if you look at it, like back to algorithm 4. It return like it return x, like, yeah. Oh, what happened? Okay, I don't know. Like ht, like if x is like on one edge, xt is gonna be non-zero on just the two endpoint of that edge. So we just really just update the weight on the endpoint of that edge. And then it just go to the next round, find the edge with the minimum weight, update the two weight of the two endpoint, and repeat. And at the end, just return like for every edge that you return, just average all of them. That's your fractional matching. That's it. That's the algorithm. So it's like kind of really like a simple looking algorithm, right? Okay. And what else? Okay. And so what's the running time? Well, row like the width is something like n at most. So this is the number of iteration. Basically, the algorithm repeat by like a number of width, like by width iteration. So this is like number of iteration. On each round, you spend linear time to find the edge with minimum weight, and then update the weights. So that takes 2 steps because there are just two nodes to update. So that's running time. And you could actually speed up the oracle just a bit, right? Because like instead of trying to like find the edge with the minimum weight by scanning through every edge on every round, you can basically, let's say you maintain the edge weight. Like for every edge, just maintain the weight. WE to be the sum of the endpoint. Maintain this for every edge. And maintain the value here in the heap or something. And on each day, you know that like there are just 2 nodes that whose weight is updated. 2 nodes U prime and V prime that you update the weights. So the number of edges, the edge whose weight is updated is at most this many. There are basically two n edges whose weight is updated. So basically on each day there are just n heap operation you need to do. So that takes like n log n times per iteration instead of m. You could make it n2, and the final running time is this one. Okay. Good. Okay. Questions? So I know I just kind of repeat things, but I hope it's clearer what's going on. Okay. So next time we're gonna see that just by applying the same framework to MaxFlow, the algorithm is gonna be so simple. It's just gonna be that for every round, you find some shortest path with respect to some weights. Like you want to solve MaxFlow, but each iteration you actually just need to find some shortest path. And then you update the weight along that path. And you're just repeating solving shortest path many times. You see that precisely why this framework allows you to solve MaxFlow using shortest path. So it's just gonna give you a new MaxFlow algorithm that is simpler than every MaxFlow algorithm that you have learned in this class. So yeah, next time you see this thing. Yeah.